Welcome all to our safety case study, which will be based upon the BP Texas oil refinery explosion, which took place on the 23rd of March 2005. This particular oil refinery employs approximately 1,800 workers, processes over 400,000 barrels of crude oil a day. This is about 3% of the total US supply. It's the third largest oil refinery in the US and the 10th largest refinery in the world. It was on this dreadful day that, due to faulty equipment and personnel not following procedures, that an enormous explosion took place that shook Texas City. 15 people died and over 100 people were injured, not to mention the damage and loss of property. As a way of introduction, I would like to announce that we will be presenting the study in four main elements. Firstly, I, Brad, will be giving an oversight of what happened. I will attempt to describe the nature of the accident and the consequences in terms of fatalities, injuries, and loss of property. You will then hear from Brian. Brian will describe the facility's normal operation and process. Element 3 will cover the cause of the accident and discuss the failure of equipment, procedures, and personnel that led to the explosion. This will be by Lindsay. Finally, and concluding the presentation, Thomas will present findings of technical improvements and lessons learned from this particular event. Okay, so let's first take a look at what happened. The accident that took place involved a part of the plant called the isomerization unit. In the month leading up to the event, the isom unit was shut down for maintenance so that repairs could be done on different parts of the unit. It was on March 23rd that the isom unit was undergoing startup to go back online and into service. According to statement of facts released by BP, the startup of the raffinite splitter within the isom unit was recognised as the most difficult, dangerous due to the introduction of hydrocarbons, elevated temperature and pressure. During startup, liquid hydrocarbons were introduced into the splitter tower. Following high-level alarm warnings, the level within the tower continued to rise until it overflowed. The excess liquid hydrocarbons were directed through a manual valve to a blow-down drum and stack, where they could be vented to the atmosphere. Due to the high temperature and pressure within the system, the level of excess hydrocarbons rose dramatically within the blow-down drum and stack, to the point where a geyser-like eruption came out from the top of the stack. The vapour cloud in the atmosphere came into contact with an ignition source, now known to be a running vehicle in the vicinity, and an enormous explosion followed. As you can see here, the area of the blast was significant. The trailers were mobile offices and people were working inside when the explosion took place. They, along with other workers in the area, lost their lives. Reports say that 15 people were killed in the accident and over 100 were injured. The explosion, blast and subsequent fires destroyed nearby cars, workshop facilities and neighbouring process equipment, as shown here.
The Texas City refinery is located just south of Houston on a property of just under 500 hectares. It contains 29 oil refining units and 4 chemical units. At full production, the refinery would produce nearly 38 million litres of fuel a day. At the refinery, crude oil is produced in various processes and stages to form different hydrocarbons, including oils, diesels, fuels, and other products. One of the refinery units converts low-octane hydrocarbons, or raffinate, into high-octane hydrocarbons via an isomerization process and plant. This is commonly referred to as the isom unit. The isom unit consists of a disulfurizer unit, reactor unit, vapour recycling and raffinate splitter. The raffinate splitter is where the accident actually occurred. The raffinate splitter utilises a fractionating column or splitter tower, feed surge drum, fire heater reboiler, overhead condenser and reflux drum. The splitter tower receives a heated feed from the surge drum via the reboiler furnace. Heat for the separation in the tower is supplied by the reboiler furnace. Overhead hydrocarbons leaving the tower travel to the reflux drum via an overhead condenser. The pressure in the drum is controlled by the furnace firing rate, and liquid from the reflux drum is pumped to the tower as reflux and then to storage. Bottom hydrocarbons from the tower either discharge through the furnace and back into the tower or to storage. Gas relief from the reflux drum travels through the blowdown system eventually to the blowdown drum and is either released to the atmosphere or to the site sewer. The instrumentation consists of high and low level alarms but no trips or emergency shutdown systems, and was monitored and controlled at the main and satellite control facilities. The refinery operated with a large number of contractors for shutdowns and maintenance, which required fluctuating levels of temporary offices and facilities. These were located as close as possible to the work areas under BP guidelines.
Now let's examine what the causes of the nature incident were. The causes have been divided up into 4 subcategories: equipment failure, procedural deviation, management failures, and personnel contributing factors. These instruments give critical information about the level and subsequent control of the unit. So how do these instruments contribute to the incident? The level transmitter had a 8% difference in its calibrated density, which caused the level to drift downwards when the process inside the tower went above its normal operating temperature, indicating that the level was falling when in actual fact the tower level was rising. The redundant high-level alarm, LAH 5102, which was the backup alarm if the other alarm did not function correctly, did not alarm when the set point of 78% was passed. These instrument failures blinded the DCS operator in making accurate decisions about the feed rate to the RAF tower. Once the tower level had reached its critical point, the PSVs lifted, releasing the process to the blowdown drum F20, and the liquid level quickly climbed to create a geyser-like eruption. Once again, the DCS operator had no idea the stack was filling up with liquid hydrocarbons because the level alarm did not function correctly. During startup of the ISOM unit and subsequent level increase in the raffinate tower, the high alarm associated with level transmitter did alarm but was ignored because of the deviation from procedure not to fill the RAF tower above the set point. In fact, the deviation was so common that in the DCS history, the level alarm can be seen on all 16 times the unit was brought back online. The written procedure stated that the level set point should be set at 50% level and the level control valve set to auto, which places the RAF tower in automatic level control. But as seen in the screenshot above, the level control loop was placed in manual, thus leaving the control up to the DCS operator. This was common practice because operators were concerned about damaging the furnace if the level was too low on the RAF tower. Cost-cutting introduced to the site when BP acquired the asset caused military process safety shortcomings in training, staffing, and asset integrity. BP's management were fully aware of employee safety concerns, and in a BP business plan prior to it, it states, TCS kills someone in the next 12 to 18 months. Then 8 days later, disaster. Throughout the investigation into the explosion and the independent safety reviews, BP management were continually at fault for not having adequate process safety. The CBS reported BP ignored numerous warnings of potential catastrophic accident as a result of not having effective reporting and learning culture. As with most serious incidents, there is a number of failures that lined up to cause the disaster. In Texas City, the failure of the personnel, the final element of the implementation of safety, failed. The shift handover between panel operators was not sufficient. Logbooks were not correctly maintained. Supervisors left site without replacements, and poor decisions in regards to the placement of contractor site officers all contributed to the cause and effect of the explosion.
Hi, my name's Tom Cummins, and I'm here to talk about the technological improvements that could have been made to the BP Texas City oil refinery. Firstly, we would like to talk about safety and technical reliability in the oil and gas industry. Safety measures are put in place primarily to ensure people can go home at the end of their shift. It is also used to save the business thousands of millions of dollars and to help protect the environment. Improving the safety culture and technical reliability of any business relies on all levels of its operations. These include its operator managers, right down to the people that are physically employed to run the operation. At the Texas City Oil Refinery, periodic auditing highlighted that a big contributor to the unsafe work culture was the cost-cutting measures. A lack of money to invest in their business adversely impacted the maintenance and infrastructure upgrades at the refinery. To emphasise how bad the safety culture was at the Texas Oil Refinery, one person every 16 months had passed away due to workplace incidents during the 30 years prior to the 2005 explosion. From there, it's just obvious that the safety culture was a significant problem well before this incident occurred. Now moving on to the mechanical improvements of the plant, we just want to highlight that this plant is exposed to very harsh conditions. A way around this is constant preventative maintenance checks. This would have highlighted the impeding problems of the ISOM unit, which could have initiated the preventative solutions to fix this part of the plant. Problems mentioned in Part 3 by Lindsay Scholes included that a high-level alarm failed, a fluid level indicator failed, and other things as well which could have contributed to the significant catastrophe. The Texas Oil Refinery was built in the 1950s. It was obvious that much of the plant was old and needed an upgrade and technical advancement. One example of an engineered improvement that could have prevented the disaster from happening in 2005 was the addition of a flare stack, which could have replaced the blowdown drum. The flare stack prevents the release of flammable liquids and vapours into the open atmosphere. Although this flare stack provides a means of an ignition, it allows the controlled release of these flammable liquids. BP actually agreed that it would eliminate all blowdown stacks by 2008 by replacing them with the flare stacks. In addition, the ISOM unit still needed some upgrades. These included a 100% fluid level indicator on both the raffinate tower and the blowdown drum, additional high-level alarms on both the raffinate tower and blowdown drum. Also, new safety rules need to be considered, such as a minimum safety distance for employees when startups occur. Mandatory fully trained and competent personnel need to be on startups and general operations. This could inhibit the fact that this catastrophe occurred. In conclusion to the report, it is worth noting that all incidents are avoidable. However, due to production's expectations and tight budgeting, it was clearly made difficult for the employees of the BP Texas City Oil Refinery to act on safety due to the lack of resources. If problems were rectified sooner than later, many incidents can be avoided, millions of dollars saved, and the impact on the environment not as substantial. Thank you for listening to our presentation.